So I'm Lysandre Follet, and I head up the Computational Design Department at Nike. It's part of the design studio. And today we're going to start with this. So this logogram translates as computer in Chinese. And what I found interesting is it actually consists of two characters, one that means electric, and the second one that means brain. So that idea of electric brain. So today we're going to look at the evolving relation between computer and designer within creative practice, or the creative collaboration between the computer, which is an electric brain, and the designer, which is an organic brain. But before, we're going to step back into the past and look at a few key moments in time. So in 1968, Doug Engelbart and the group of 17 researchers working with him in the augmentation research lab at Stanford presented a 90-minute live public demonstration of a system that was showing augmentation of human with the interface with the computer. So they invented the mouse and a lot of devices like that that really allowed the computer at the beginning to take off. To note that at the same time as Stanford, there was also a lab talking about artificial intelligence. But what Doug and his colleague was really focused on is that idea of augmenting intelligence and not replacing it. And Doug Engelbart has a really nice quote in 1962. He said that a tool doesn't just make something easier, it allows for new, previously impossible way of thinking, of living, and being. In 1997, after a few years of research and development, IBM built Deep Blue, a state-of-the-art computer that was designed to run powerful algorithms to play chess against the best player in the world. May 11, 1997, Deep Blue is set for an historic game, and we all remember what happened that day. Deep Blue beat the world chess champion after a 6-game match. 2 wins for IBM, 1 for the champion. What is less known is that following that defeat, Garry Kasparov started to look into recognizing the potential of such an advanced computer system, not just as a human versus computer, but as a way to set up a partner in the game. And he designed that idea of advanced chess that is sometimes also called cyborg chess or centered chess. And the idea is that the objective of a human player on a computer chess program playing as a team. So not against each other, but really augmenting each other. And many top-level players have seen a lot of benefit from that. It does produce blunder-free game with the qualities and the beauties of both perfect tactical play and highly meaningful strategic plans. And it gives the viewing audience an insight into the thought processes of strong human chess player and strong chess computer. So kind of the best of both worlds, of that organic brain and that electric brain. So I think at that time, people started to understand what an algorithm meant, and also demonstrating that we could go beyond utilitarian application, but start to tackle more complex tasks like creativity. And today, we have algorithm everywhere in our pocket. And I think this is a powerful demonstration of what algorithm combined with advanced robotic can do. Making a handstand will probably take you hours of yoga practice before you can even handle that. And this guy just make it look really easy. So this is pretty interesting. What I'm interested to talk about today is how we can leverage those same powerful concepts and methods to radically change the way we design footwear and product at Nike, on how they become more and more personalized. But before we do so, let's look a little bit about history of Nike. At Nike, from the beginning, we've always been a crafter, innovator, and maker. And in the late 1950s, one of our co-founders, Bill Bowerman, was a coach at the University of Oregon. And he was really interested in trying to understand about individual specific for each athlete. So he will measure the feet of his athlete, he will take notes, he will shave grams from the shoe, he will adapt them. So kind of doing personalized footwear, but with very analog tool at the time. Our mission statement is to bring inspiration and innovation to every athlete in the world. And what we mean by that is it's not only for professional athletes, but all athletes. So if you have a body, you're an athlete. So how do we design for every athlete in the world? Well, it's complicated because we all have very different body. Most of the time, our left foot is also different from the right foot. And for the last decade, as we design product, we have optimized against sample size. So we design for one size, and then we just scale it up and down. It's as good as it can get with that method, and it's often, it often doesn't fit perfectly. Performance isn't perfected, but it really is as good as we can get with traditional method. So how do we go from designing from average to designing for a batch of one? So in 2013, we started to work with Jamaican Shelly Ann Fraser-Price. She's a sprinter, a high-cadence sprinter. And the goal was to build for her the best spike, the best shoe. And it was interesting because Shelly Ann is size 5, which is a small fit. So it's a good test subject for us to try to reinvent the product. So at Nike, we spend a considerable amount of time to listen to the voice of the athlete. We put them at the center of the design process, and we gather a lot of data on them. And I'm going to show you a sneak peek at how we do that back in Portland with the Sports Science Lab.
If you take science and design by themselves, they have no power. They're not going to do beautiful things, but the overlap and the convergence of those two together, it's when beautiful things happen. It's an extremely creative process to be a researcher in the Nike Sport Research Lab. If you look at all of us, we're all extremely passionate about sport. We geek out on the science of athletes and athletic performance. Every day is a new challenge, and we want to make athletes better all the time. Athletes ask us for 3 things. They ask us to make me better, to protect me, and to inform me. The better you understand the needs of that athlete, the better you're going to make product. Motion capture is one of the tools we use. What it allows us to do is really objectively understand an athlete in motion. We use high-speed video. Most digital cameras capture around 30 frames a second. We can do 30,000 frames a second, so we can see things you don't necessarily see with the naked eye. Our force plates take thousands of measurements per second, and we get forces in 3-dimensional space. We have environmental chambers. We can collect things like expired gases, so we know the amount of energy your body is using to do a particular movement. And in these chambers, we can accurately replicate weather from anywhere on the planet and make sure that our product is going to work in those environments.
So as you can see, we collect tons of data, which are really interesting, but it's often very hard for us to make sense of it with traditional design methods. So how do we best leverage data to inform design? Well, most of the creative software for the last decade have been replicating traditional design processes. They often just kind of give you the experience of drafting, sculpting, but there is a loss of translation and a loss of information. It's hard to make sense of the data when you use that type of design method. And it's kind of a byproduct of what CAD has been for the last 10 years. It stands for computer-aided design, and it's really meant to increase the productivity, but not that much enhancing or augmenting creativity. So in 2012 at Nike, we started to look at computational design, and I always like to go back to the Wikipedia definition, which say that computational design is the application of computational strategy to the design process. So using algorithm to define the steps that create the product. And the goal really isn't to define the final result, but rather all the steps that create that solution space. So computational design has been heavily used by architects, and in the last 5 years, we've seen it being adopted in industrial design, medical fields, and tons of other areas. And we often find 3 components: a design schema, a means of creating variation, and a means of selecting desirable outcome. And I'm going to unpack that for you. So the first step is data collection. So we went back into the lab, brought back Shelly Ann, and as you saw, we can have force plates, in-shoe pressure, and motion capture. So what that allowed us is by placing sensor in the shoe, we were able to track how much forces Shelly Ann apply on each stride. And once the researcher finished analyzing the data, we could start to have some strategy to build our algorithm. We needed to be able to create a tunable sprint plate with a structure that will be at the same time light and stiff where it needs to be. So step 2 of a computational design process is translating that design problem into computational computable parameters or constraint in the generative objective. And for that, we look at nature for guidance, and we found these planktonic diatoms, which has a really interesting structure. So if you look at the architecture, he has that system that allowed him to be light and stiff at the same time. So he's really managing that complex problematic. And we look for the principle on architecture of that organism, and we start to shape the design process by writing algorithms that describe how the design gets constructed. And then it's that idea of building a tool versus using a tool. We are translating design ID into computational parameter, and it allowed us to really think in a new way, creating and making. The step 3 is creating variation. So once we have the algorithm and the system in place, we can start to explore design space and create variation. We can experiment with parameter and make adjustment to the algorithm to create variation. This kind of gives you an idea, a little bit of the behind the hood of the system. It's a dynamic and fluid system, and the designer and the algorithm are working together to translate this understanding of the complexity. So this really treats the data and the structure pattern as data not in a static spreadsheet, but as a living ecosystem, as you can see. That gets translated into a variable stiffness 3-dimensional structure that allowed us to precisely put stiffness where we did. The last step, and maybe the most fun part for creative, is exploring design space. So it's a very different approach because we have that dynamic system that we can interact with. Every time we run the algorithm, we generate thousands of solutions that we can explore. It's very stimulating for the brain. This is a drone chassis exploration from software company Autodesk. And what you see here is the design solution space being navigated by the designer with different solutions that all match the problem. We have endless possibility, and we can unlock imagination. Design space are huge, so we kind of have to have some strategy to search them. And one of the things that we do a lot at Nike is using computer simulation. So we can simulate what will happen in real life and understand a little bit what's happening to the product before we even make the product. It allowed us to remove a solution from the design space and start to narrow down to find the best possible solution to our problem. And of course, leveraging new method of make, such as 3D printing, we can very quickly produce a product and put it on the feet of the athlete. So that's our second method of validation, is real-life testing. This is a photo of the first spike that we printed at Nike, and this allowed us to really shorten the design cycle because we can print overnight instead of having to wait weeks or months for a sample to come back from Asia. We can test it on the athlete feet, gather new data, and feed back that data into the algorithm to create a new iteration to get to an always better product. So the role of the designer at this stage in that new paradigm really become more a role of curator. It's about reframing subjective human preferences, such as comfort, performance, criteria combined with aesthetic. So augmented by the computer, the designer really take on that new role of curator. And this is where we landed with the product for the Rio Olympic. And with computational design at Nike, we have solved one of the most challenging problems we ever had. I talked a little bit about that idea that we used to design for one size and scale it up and down. So we kind of revisited that for Rio. Those are 4 world-class athletes, and at that point in time, they're all running the same distance. It's 100 meters. The difference is they all have different feet size. So as I told you, we will normally design for size 10 and scale it up and down. So the size 5 will be out of spec, probably too soft or too rigid, and the 12.5 same. So this time around, we went back to the algorithm and changed the parameter, understand the data for each athlete, and were able to generate a family of products. So if you look at them from far, you can see that they look like a family. They share that same DNA. But if you look in the detail, you see that the structure and the system has adapted to create stiffness and just what you need per size. What we also did is look at distance. So in track and field, what's interesting is you go from 100 meters to 10K. And what you're really doing is you're going from running straight to starting to run around the stadium. So we run the same exercise, look at the data, and try to understand how can we have the algorithm create a unique possible solution. And that's where we landed. So as you can see, as you go through the curve, the structures start to open to allow for medial to lateral flexion as you take the curve. And for the 10K, it becomes as minimal as it can get, just to provide you traction where you need. Those are some of the beauty shots from the Rio Olympic. And we couldn't have dreamt of a better stage. After 3 years of hard work, the performance of the product got validated on the track with more than 45 medals on helping athletes achieve their dream. And finally, we leveraged the very same algorithm, creating solutions across the full spectrum of product for the business. So this is American football, and we're already solving the same problem. We want something that is stiff and light at the same time, and also that allowed to play for the specific of the sport. And then also build a baseball clit out of the same algorithm. So they're really just a mutation of the same system, and that's what I want you to take away today, is that idea of algorithm that create a non-finite solution space, and that then can get tuned for very specific application. So in this creative process, the computer generates thousands of design solutions that the designer on his own would have never envisioned, as well as many creative artifacts. And I think that's really that idea of the computer become a partner in creation, very similar to Gary Kasparov's original idea. We are augmenting creativity, and we are getting into that sort of co-creation relation with the computer. And today I want to finish on a quote from Lysandre after playing against and being defeated by AlphaGo. And Lysandre say, AlphaGo showed us that moves humans may have thought are creative were actually conventional. I think this will bring a new paradigm to go.